This video series is about Infra-Bayesianism, and in order to understand Infra-Bayesianism, it's useful to understand what classical, straight-up vanilla Bayesianism is. In this video, we're just going to scratch the surface of what Bayesianism is, and we're just going to get a small taste of the power that Bayesianism has to help people reason effectively about a broad range of topics. But Bayesianism is a mathematically rigorous procedure for updating one's beliefs after observing data or evidence. The procedure is essentially just an application of Bayes' theorem, which you can see here on the screen and which we'll go into much more detail later in just a few minutes. Bayes' theorem was discovered by the Presbyterian minister Thomas Bayes in the 18th century, and it's not too controversial to say that Bayes' theorem is the most important theorem in all of probability theory. Now, let's start getting into the nuts and bolts of Bayes' theorem. First, we need to talk about what conditional probabilities are. Suppose that you have a coin. We can talk about the probability of a specific event occurring. For instance, the probability that the coin will come up heads, in blue here. If the coin is fair, this probability would be 0.5 or 50%. All right, we could say that the P of heads is 0.5 or 50%. We can also talk about the probability of some event B occurring, given that we have knowledge that event A has already occurred. This is called the conditional probability of B given A, or the probability of B conditioned on A, or the probability of B given A, right? And the idea here is that we want to have some notion of saying the probability of event B happening, given that we know that event A has already happened. For example, suppose that you roll a fair six-sided die, and you get a 2. What's the probability that your next roll will be a 5? Dice rolls are what we call independent, which means that the knowledge that we just rolled a 2 doesn't give us any further information about what the next roll will be. So the probability of rolling a 5, given that we just rolled a 2, this probability here, is just the same as the probability of rolling 5, right? So this is just 1 in 6. Let's contrast this with this second example, where the two events are not independent, but rather they're dependent. There are 8 marbles in a jar, 5 green and 3 red. You pull one out randomly and it's red. What's the probability that on the next pull you'll get a green marble? Well, if we hadn't already pulled out any marbles from the jar, the probability of pulling out a green marble would be 5/8. But since we have already set one of the red marbles aside, the conditional probability is 5/7. Right? The probability of pulling a green marble on your second pull, given that you pulled a red marble on your first pull, is 5/7. Okay, now that we have a basic handle on conditional probabilities, let's keep moving forward towards understanding Bayes' theorem. Given the same setup as before, the 8 marble jar scenario, what's the probability of pulling 2 green marbles in a row? This notation here, this little kind of horseshoe shape, means the probability of pulling a green marble on your first pull and pulling a green marble on your second pull. So this upside down horseshoe means and. So, well, the probability of pulling a green marble on the first pull is 5/8. So if I can just write up here, the probability of pulling a green marble on your first pull is 5/8, okay? And the probability of pulling a green marble on your second pull, given that you already pulled a green marble on your first pull, right? Now you have 4 green marbles out of 7 marbles total, so it's just 4/7. So now the probability of putting this all together, right? The probability of getting a green marble on both your first and second pull is just the probability of pulling a green marble first times the probability of pulling a green marble second, given that you already pulled a green marble on your first pull, okay? Right? So we multiply these two probabilities together and we get 5/8 times 4/7, which comes out to 5/14. This example is meant to illustrate that the probability of A and B, right? Event A happening and event B happening, is just the probability of event A happening times the probability of event B happening given that A just happened. So now we're really ready to derive Bayes' theorem. That's really all we need. Is that the probability of A and B is equivalent to this, what we just saw above, and the probability of B given A is equivalent to this. Well, the probability of A and B is the same as the probability of B and A, right? These are equivalent. So I can really set this expression and this expression equal to one another. Now, if I just divide both sides by the probability of B, I get that the probability of A given B is the probability of B given A times the probability of A over the probability of B. I just divided both sides of that equation by probability of B. Now this is Bayes' theorem. Now, let's apply Bayes' theorem to see how it works, to help us update. All right, so we've got an example here where there are 3 types of coins which have different probabilities of landing heads when tossed, right? Coin A, or type A coins are fair, meaning that they have a 50-50 chance of heads versus tails. Type B coins are not fair. They're biased towards heads at 60% heads, and type C coins are even more biased towards heads at 90%. Suppose I have a drawer containing 5 coins, 2 type A, 2 type B, and 1 type C. I reach in the drawer, pick a coin at random. Without showing you the coin, I flip it once and I get heads. What's the probability that this coin is type A, type B, or type C? Okay, so this is a classic Bayesian updating problem. And we're going to use Bayes' theorem in order to calculate these probabilities, the probability that the coin is type A, type B, or type C. Okay. Now, we need to introduce some vocabulary here that comes up super often when we're using Bayesian updating. First, in this example, we have 3 hypotheses. The coin is of type A. And we could also have another hypothesis that the coin is of type B or the coin is of type C. So in this example, we're considering 3 hypotheses. Just for short, I'm going to call these hypotheses A, B, and C. Now, for each of these 3 hypotheses, we have a prior probability that the hypothesis is correct. Without observing any data, I might say the probability of picking coin A from a coin of type A from the drawer is just 2/5, right? Because I have 2 coins of type A, 2 coins of type A, and there are, 2 plus 2 plus 1, 5 total coins, so that's 2/5, or 0.4, right? So for A, probability of A, the prior probability of A is 0.4. Likewise, the prior probability of B is also 0.4, and the prior probability of C is 1/5 or 0.2. Prior to receiving any data, what's the probability that the coin is of type A? Well, it's just, there are 2 coins out of 5 that are of type A, so the best we can do is say, all right, my prior probability of the coin being type A is 0.4. Okay, now the data is just heads. In this case, we're told that we flip the coin and it lands heads. We're going to use that data to eventually update our prior probabilities to better probabilities to reflect that data. Once we get data, we can compute the likelihood, the conditional probability of observing the data, assuming that a given hypothesis is true, right? So each of these hypotheses is going to have a likelihood. And I can say the probability of heads, the probability of observing the data, given that my hypothesis is true, right? So the probability of heads given A. All right, so if A is the type of coin that we flipped, right? A is a fair coin with 0.5 chance of heads. So the probability of observing a heads, given that the coin is A, well, that's just 1/2. It's just 0.5, right? Now the probability of heads given B, the likelihood for hypothesis B, is 0.6. And the likelihood for coin C is, you guessed it, 0.9. So those are our likelihoods. And the goal is to come up with posterior probabilities, right? The probability of hypothesis A given that a heads was flipped, the probability of B given that a heads was flipped, and the probability of C given that we got heads. That's the goal. And we're going to use Bayes' rule, Bayes' theorem, to compute those posterior probabilities. We can organize these probabilities, this information, into a Bayesian updating table here, where I've got all my hypotheses here, my priors, and my likelihoods, and the goal is to fill in this posterior column. I can also organize all of this information into a probability tree. And we're going to use this probability tree to calculate our posterior probabilities. All right, so let's start finding the posterior probability for hypothesis A. So the probability of A given that I flipped heads. Well, we know let me just write out Bayes' theorem. The probability of, going back to our example, the probability of hypothesis A being true, given that we flipped heads. All right, I can just use Bayes' theorem here, and I can say this is the probability of heads given A times the probability of hypothesis A, the prior probability of hypothesis A, over the probability of flipping heads. All right. Now let me just write out the same thing for all of the other hypotheses. Okay. So now we're all set up. You'll notice that for each of these, I have everything I need to calculate the numerators. All right. Let's go ahead and fill in the numerators. Right. We can go back to we can use our tree here and say the probability of A, right? The probability of A, the prior probability is 0.4. So I'll change this to 0.4. And the probability of heads given A, right? That's this probability that's right here on this branch of the tree. So that's 0.5. That's the likelihood associated with hypothesis A. Okay, and we'll look at probability of heads in just a second. Let's just fill this in for B as well. There we go. Okay, now let's talk about the probability of heads. Now, don't worry too much about how the probability of heads gets calculated, the Bayes denominator. We use something called the total law of probability, and I'll just show you how that gets calculated. The probability of heads is we go down here and we look at every node that has heads beside it, and we backtrack up the tree all the way to the top node, multiplying each of these probabilities together, right? There is an intuitive reason for why this makes sense to do in order to calculate the probability of heads, but that's outside of the scope of this video. So the probability of heads is going to be 0.5 times 0.4, and then we're going to add, right, I just multiplied these two together. I'm going to add that to 0.6 times 0.4, and I'm going to add that to 0.9 times 0.2. This comes out to 0.62. So the denominator here, in every case, is 0.62. Okay, and now we can calculate all of these and we can fill in our posterior probabilities. Okay, so we can use Bayes' rule to update all of our prior probabilities to posterior probabilities. Now, one thing I want to emphasize here is that let's say that we keep flipping the coin. We flip it a lot of times, right? Maybe 100 times. On the next flip of the coin, let's say that I flip the coin again and I got tails, right? I could make a new table, right? And I could use these posterior probabilities that I got after the first flip, and I could use those as a new prior probability and calculate different posteriors given new data, right? And we could continue to do this over and over until we converged to the correct coin type. Okay, so Bayesian updating allows us to, given enough data and evidence, Bayesian updating will converge to the correct hypothesis. Okay, so eventually, given enough data, given enough coin flips, we'll be able to figure out which of these hypotheses is actually true. All right, let's do one more example of how Bayesian updating works. This time I actually encourage you to pause the video and try to solve this problem on your own. Once you're finished, unpause the video and watch the solution. Okay, so let's start to make a Bayesian updating table. All right, so I'll use H for hypothesis. So I'll use P of H for the prior. I will use the probability of the data given the hypothesis for the likelihood, and the probability of the hypothesis given the data for the posterior. I really only need to entertain two hypotheses here, right? One hypothesis is that the person has the disease, right? And the other hypothesis is that the person doesn't have the disease, right? Positive and negative. Okay. What is the probability that the person has the disease prior to observing any data? Well, the prevalence of the disease in the general population is 0.5% or 0.005. So that is the probability that a randomly chosen person would have the disease. Right? So it's 0.005. And so this needs to be 1 minus 0.005 or 0.995. Now the likelihood, the probability of the data. Okay, so what's the data in this case? Well, the data is that our randomly chosen person tests positive. Really what I could say is I could replace this D for data with, they test positive. Okay, all right. So what's the probability of I'll come up here and write the probability of testing positive given that a person has the disease. Well, that's just the true positive rate, right? The true positive rate is 99%, so I can write 0.99 here. All right. Now, what about the probability of testing positive given that the person doesn't actually have the disease, right? That's a false positive rate. You got a false positive test, so that's 0.02. Let's calculate the probability that the person has the disease given that they tested positive. Well, using Bayes' theorem, that's the probability they test positive given that they have the disease times the probability that they have the disease, the prior probability that they have the disease, all over the probability that they test positive. We have the numerator. We have everything that we need for the numerator, okay? And now what about the denominator? Well, let's go back to our tree. Let's draw a tree here. All right, so we can now calculate the denominator using the total law of probability. We just go to each bottom node and backtrack up the tree. And if we do this, it comes out to about 20%. Okay, all right. So this is approximately 20%, which means that this one has to be about 80%. So far, we've only considered discrete priors, where there are only finitely many hypotheses to consider. For instance, in the previous example, we only had to consider two hypotheses, right? The hypothesis that someone has the disease or doesn't have the disease. What about continuous priors? What if there are infinitely many hypotheses? For instance, let's say that you have a coin with some probability theta of coming up heads, where theta is between 0 and 1. In this case, your prior is a continuous function. For instance, let's just make up a prior here. Maybe the prior is 2 theta, right? Theta could be anything between 0 and 1, right? There's infinitely many possibilities for the prior. You flip the coin and it comes up heads. How do you update? This kind of problem is beyond the scope of this video series, but rest assured that Bayesianism is fully capable of dealing with continuous priors. We just use some calculus. The same is true for cases where the data is continuous. We've only considered cases where there are finitely many possibilities for what the data could look like. The test could either be positive or negative, or the coin could either come up heads or tails, right? But what if there are infinitely many possible forms that the data can take? No problem. Bayesianism deals with this case using calculus as well. What about cases where the prior probabilities are unknown? Okay, so for instance, suppose we have a drawer full of dice, each of which has either 4, 6, 8, 12, or 20 sides. This time, we do not know how many of each type are in the drawer. Okay, you don't have a prior probability distribution that's given to you. A die is picked at random from the drawer and rolled 5 times. We get these results, and we want to update. Right? What do you do here? When the prior is known with certainty, all statisticians will gladly use Bayes' theorem. Okay, like we've been using. But once the prior is unknown, two schools of thought begin to emerge. The Bayesian school decides to come up with a plausible prior and use that for updating. Right? Bayesians will also often test several plausible priors to see if they point to the same conclusion. And Bayesians will always justify their reasoning for choosing a specific prior to reason with. Right? So let's look at a few examples of how various priors will affect the posterior probabilities in this example above with the multiple dice. So you can see here that we've chosen a uniform or flat prior, where we've just said, I have no idea how many of each type of die are in the drawer, so I'm just going to assign a 1/5 probability to prior probability to all of them. Well, in this case, the D8, the 8-sided die dominates, right, with above 85% probability. What if I say, I'm going to use a different prior. I have good reason to suspect that there are 10 times as many D20s, 20-sided dice, in the drawer as any other type of die. Right? And you can see that reflected in the priors here. Well, still in this case, the D8 is very, very likely, but the posterior probability for the 20-sided die has gone up considerably compared to when we used a uniform prior. If you have good reason to suspect that there are 100 times as many D20s as any other type of die, you use a different prior, right? Then things start looking interesting. All of a sudden, the 20-sided die, even with this data, even with, what data did we have? Even with this data, right, which seems like this data wouldn't come from a D20, if you have such a strong prior probability placed on the 20-sided die, the 20-sided die can still be the most likely one. All right. Now, on the other hand, as soon as the prior is unknown, as soon as we get to cases where the prior is unknown, frequentist statisticians will abandon Bayes' theorem and priors altogether and make inferences based only on the likelihood. Okay, don't worry too much about what I mean by making inferences based only on the likelihood. The main point is that they don't use Bayes' theorem and they don't try to use priors anymore. If you've heard of these statistical terms before, things like null hypothesis, significance testing, t-test, confidence interval, p-value, type 1 error, type 2 error, these all come from the frequentist approach to statistics rather than the Bayesian approach. Now, another way to distinguish between frequentist and Bayesian approaches to probability and statistics is to say that whereas frequentists are uncomfortable with the idea of using probabilities to express subjective degrees of belief that could differ from one statistician to another, Bayesians are perfectly comfortable doing so. Okay, so for instance, a Bayesian is perfectly fine saying something like, there's a 95% chance that the number of people with red hair in the United States is over 5 million. A frequentist would consider this an inappropriate application of probability. They would say that the number of people with red hair in the United States must be some fixed number. So it doesn't make sense to assign any uncertainty, any probability to a fixed number. Frequentist statistics was developed in large part by R.A. Fisher, and it dominated science during the 20th century. Now, E.T. Jaynes here on the right is the most prominent Bayesian statistical theorist of the 20th century, and his book, Probability Theory, The Logic of Science, had a tremendous impact on the scientific community. Prior to this book, the conversation about frequentism versus Bayesianism mainly involved people saying that it was a matter of taste, whether you were a frequentist or a Bayesian, and that in cases where the prior is uncertain, statistics becomes an art where either Bayesianism or frequentism will suffice. The reason that so many people used frequentism in the 20th century and even into the 21st century is that it's way computationally less intensive than Bayesian updating is. Okay, but Bayesian updating has seen wider adoption in the scientific community in the 21st century since now we have access to way more computational power. But in this book, Jaynes uses a few ingenious mathematical moves to show that the choice between frequentism and Bayesianism isn't a matter of taste or art, but rather a matter of whether or not you want to be logically sound and mathematically consistent, right? So he unleashes a devastating critique of frequentist statistics and derives some inconsistencies in several of the techniques of frequentist statistics, several of these techniques that I wrote about up here, null hypothesis, significant testing, t-tests, confidence intervals, things like that. Okay. Now, Jaynes' book has significantly influenced several prominent members of the effective altruism community. You'll hear a lot about Bayesianism and Bayes' rule if you frequent effective altruist circles. So, for instance, here's John Wentworth quoting from his study guide. Jaynes' Probability Theory, The Logic of Science is a book for which I know no substitute. It is a book on Bayesian probability theory by the leading Bayesian probability theorist of the 20th century. Other books on the topic look sloppy by comparison. There are insights in this book which I have yet to find in any other book or course. At a bare minimum, read chapters 1 through 4 and chapter 20. I've read it cover to cover and found it immensely valuable. Eliezer Yudkowsky in 2008 said, I aspire to Jaynes' level. I aspire to become as much the master of artificial intelligence as Jaynes was master of Bayesian probability theory. I could even plead that the art I'm trying to master is more difficult than Jaynes, making a mockery of deference. Even so, there is no art of which I am as much a master now as Jaynes was of probability theory. So I hope you're getting the sense that people are impressed when they read Jaynes' book on probability theory. All right, if you want to learn more about Bayesianism, I would suggest these three resources. MIT Open Courseware has published a full course on probability and statistics, which is what I used for self-study to build up a basic understanding of probability and statistics. If you want to, you can go read Jaynes' book. You can also check out Aubrey. Clayton has a YouTube series called Probability Theory, The Logic of Science. And the introductory video is quite good at laying out what Jaynes' book is all about. All three of these resources will be linked in the description. Now that you have a general understanding of what Bayesianism is all about and have an appreciation for its power, you might be wondering to yourself why we need Infra-Bayesianism. As you've heard several times during this video series, there is a particular problem called non-realizability that kept popping up in theoretical AI safety research. Now, don't worry, we'll be defining non-realizability soon. What's important to appreciate now is that Bayesianism is insufficient for dealing with the problem of non-realizability. Infra-Bayesianism was invented to improve on Bayesian reasoning to get around the problem of non-realizability. We'll be looking at this in much more detail very soon.